Welcome to my channel Phi Concepts CHM. This is the fifth part of the series of thermodynamics, where we will see the applications of first law of thermodynamics. Here we will see the heat capacity, the specific heat of ideal gas. Heat capacity. Different materials have different capacity to absorb heat to produce a given change of temperature in a given mass. If a material of mass m absorbs heat Q so that its temperature rises through delta T, then the heat capacity can be given as Q upon delta T. Specific heat. It is the heat capacity per unit mass. We write down the formula as C is equal to Q upon M into delta T. Specific heat of a material is defined as the quantity of heat required to raise the temperature of unit mass of the material to 1 degree. The unit in CGS is calories per gram per degree Celsius. In SI units, it is joules per kg per degree Celsius. This definition is sufficient for solids and liquids. Since the gases are compressible, the specific heat of a gas may vary from 0 to infinity. For example, if a gas is compressed, its temperature rises without supplying any heat to it, that is, Q is equal to 0. Therefore, the specific heat C is equal to 0. On the contrary, if the gas is allowed to expand without any rise in temperature, that is delta T is equal to 0, then C will be equal to infinity. Since gases are compressible, C ranges from 0 to infinity. So for gases, the two specific heats are important. One is the specific heat at constant pressure, that is C suffix P, and specific heat at constant volume, C suffix V. Specific heat at constant pressure. It is the amount of heat required to raise the temperature of unit mass of a gas through 1 degree Celsius when its pressure is kept constant. It is given as Cp is equal to delta Q upon delta T at constant P. Equation P. Then specific heat at constant volume is the amount of heat required to raise the temperature of unit mass of a gas to 1 degree Celsius when its volume is kept constant. Cv is equal to delta Q upon delta T at constant volume. Equation Q. We will show Cp is greater than Cv. Heat capacity of a gas is different under these two conditions. The two conditions, one at constant pressure, the another at constant volume. Suppose we'll take the first case, gas is heated at constant pressure. Then the gas is allowed to expand. Heat supplied is used up for, first it raises the temperature of the gas, that is increase in its internal energy. it does work in expanding the gas against the external pressure. So delta Q is equal to du plus delta W. We can substitute delta W as PdV. Second case, gas is heated at constant volume. So dV is 0. So PdV is equal to 0. That is delta W, the work done, is equal to 0. Therefore, the whole heat supplied is used to raise its temperature. That means more heat is required for increasing the temperature of the gas through 1 degree Celsius at constant pressure than at constant volume. Therefore, Cp is greater than Cv. Now we will start with the applications of first law of thermodynamics. First application, specific heat of ideal gas. Take n moles of ideal gas. If you keep volume of the gas constant, all the heat supplied goes towards raising the temperature dT. The gas is not allowed to expand and it does no work. Therefore, dQ is equal to du plus PdV, where dQ will be the amount of heat absorbed by the gas. So we can write down from equation Q, dQ is equal to N into Cv into dt. This is equation Q. Du is equal to the net change of internal energy of the gas. So we can substitute dQ as NCV dt is equal to du plus work done is 0. PdV is 0. Therefore, we get du is equal to NCV dt, equation 1. Again, take n moles of gas, heat it at constant pressure to increase the temperature by the same amount dt. Some amount of the heat is supplied, it goes for doing the external work, and only a part of it goes towards raising the temperature dT of the gas. Now we will use equation P. Cp is equal to delta Q by delta T at constant P. So we get dQ is equal to N into Cp dt, equation 2. dW is the work done, that is PdV, and also we'll substitute equation 1 that we have got in the first law of thermodynamics, this equation. We get NCP dt is equal to NCV dt plus PdV, equation 3. Now for an ideal gas, PV is equal to nRT at constant pressure. We can write down PdV is equal to nR into dt. Substitute this in equation 3. We have substituted PdV over here, that is nR dt. Then NCV dt is taken on this side. So NCP dt minus NCV dt is equal to nR dt. You can divide the equation throughout by n dt. You get Cp minus Cv is equal to R. R is the gas constant. And also from this equation what we can understand is that Cp is greater than Cv, which is a Mayer's relation. Okay, it gives a relation between the two specific heats. Also, by using the first law of thermodynamics from equation 1, du is equal to Cv dt. Since dV is equal to 0 when the volume is constant. We can write down Cv is equal to delta U by delta T at a constant volume. For an ideal gas, the internal energy U is just a function of temperature only. So we can write this equation as Cv is equal to du by dt at a constant volume. Thank you for watching this video.